Alrighty, so tonight we're going to be learning about thermochemistry, which includes some review and then an introduction to new material. So let's take a look at what thermochemistry is. Thermochemistry is the study of energy changes occurring during chemical reactions and changes in state. Now, every substance has an amount of energy stored inside of it. This energy, which is stored in the chemical bonds of a substance, is called chemical potential energy. During a chemical reaction, a substance is going to be transformed into another substance with a different amount of chemical potential energy. Excess chemical potential energy is then transformed into work, heat transfer, or a combination of both. So when you're looking at a chemical reaction, what's happening is that the chemical potential energy of one substance, when it goes and becomes a new substance, is transformed. And it becomes this new substance with a new chemical potential energy, and any excess potential energy that you get from that transformation becomes work, heat transfer, or a combination of the both. So let's talk a little bit. We just mentioned something called potential energy, and let's talk and explain what that means. So we have kinetic energy and we have potential energy, and we've talked a little bit about kinetic energy in class before. We've talked about kinetic molecular theory, which kind of involves kinetic energy, but we haven't really talked about potential energy before. So kinetic energy is energy due to movement, or energy of movement, whereas potential energy is the energy stored within an object. It is the energy, it's kind of, kinetic versus potential energy is kind of the seen energy versus the unseen energy. Kinetic energy is obvious. We get it. We see it. It happens when things are moving. Potential energy is energy that's there that just hasn't been released yet. And so it's the energy, it's the potential of the energy. So it's energy that's kind of just waiting to be released. Kinetic energy is released due to movement, and potential energy is released under the right conditions, like a chemical reaction, for example. So let's talk about heat, and you guys will remember heat. Heat is represented by the letter Q. We learned all about that back in Unit 4. And heat is the energy that is transferred from one object to another due to a difference in temperature. So heat always flows from the warmer object towards the colder object. So heat is energy transfer due to a difference in temperature, and heat always flows from warmer to cooler. Just like in biology, when you learned about diffusion and how you're going to diffuse from the more concentrated to the less concentrated, it's kind of like that. If two objects are touching, energy will continue to transfer from the warmer object to the colder object until the two objects have the same temperature, or what we call thermal equilibrium. So this transfer of energy is going to go until both objects reach what we call the thermal equilibrium, or the same temperature. Okay? So let's talk about the difference between heat versus temperature, because there can be a little bit of confusion. So heat is an extensive property versus temperature, which is an intensive property. And what this means is that heat is dependent on the amount of a substance, whereas temperature is independent of the amount. So the best way to kind of describe this is if you have a little teeny tiny teacup of boiling water or a giant cauldron of boiling water, the temperature of the water that is boiling is independent on how much water there is present. The temperature of both of those, the teeny tiny teacup versus the cauldron, the temperature of both sets of water is going to be 100 degrees Celsius if it's boiling. It doesn't matter that there's much less water in the teacup than there is in the cauldron. Okay? Heat, the heat of those solutions would be something completely different. Heat is the energy transfer from hot to cold, whereas temperature is just the temperature of an object. So just the, I don't know how to describe temperature without using the word temperature, which is awful. But it's just the temperature of an object, just the feel of it, how warm or cold it is. Okay. Now let's talk about some key terms that we're going to be using from now on when we talk about heat. And one of those is describing things in terms of something called the system. And the system is the part of the universe on which you're focusing your attention. So when we talk about heat, we're going to start talking about a universe. And the universe has two parts, and one of them is the system. And the system is the actual part of the universe that you're focusing your attention on. It's the actual chemical reaction, or the actual phase change, or what have you. And the surroundings is the rest of the universe. So, or more specifically, the region in the immediate vicinity of the system. So when you have the universe, you have system plus surroundings. System is the chemical reaction or phase change or whatever that you're focusing on. The surroundings is pretty much everything else. In an exothermic process, we release heat to the surroundings, so from the system to the surroundings. In an endothermic process, we absorb heat from the surroundings into the system. So these are going to be different things that we talk about a lot about: system and surroundings, exothermic and endothermic. Okay, and I know that we're moving really, really fast, and you might have to go back and pause things, but we've got a lot to cover. So let's recap specific heat a little bit. So specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And we have written it in the past as Q equals mc delta T. But now we're going to involve some of that terminology that we just talked about of system and surrounding. And the specific heat that we were talking about was actually the Q of surrounding is equal to mc delta T. And the reason why we use surrounding, not system, is because the system is in fact too small to actually measure, right? If you're looking at a reaction, the area that the reaction is actually occurring is much, much smaller than the solutions mixing together. And so that is technically what we're measuring is Q of the surroundings, not actually Q of the system. The system is happening on a microscopic level with molecules actually interacting together. That's not what we're measuring the temperature of. We're measuring the temperature of the surroundings. So from now on, you'll not be able to just write Q. You're going to have to tell me whether it's Q of the system or Q of surroundings. Substances with low specific heats are much more affected by heat than those with high specific heat. So for example, things that conduct heat or electricity well have low specific heat, like metals, versus things that require a lot of heat to warm up, having high specific heats, like water or wood. Water has a specific heat of 4.18 joules per gram degree Celsius, whereas copper or aluminum has a specific heat of 0.9 joules per gram degree Celsius. So 4.18 versus 0.19. Again, things with low specific heats are much more affected by heat than those with high specific heats. And in specific heat, we talked a lot about calorimetry, which is the precise measurement of heat flow into or out of a system. Now, when we're talking about specific heat and doing that kind of stuff and talking about heat, we're mostly describing calorimetry or calorimetric experiments where you're trying to find the heat of something based on the specific heat equation, Q equals mc delta T. Okay? With that in mind, heat released by the system is equal to the heat absorbed by the surroundings. This is a whole universe that we're looking at. Sorry guys, that was my thumb. This is a whole universe that we're looking at, and heat energy cannot be created or destroyed. So anything that's released by the system must be equal to what was absorbed by the surroundings. We can't create it or destroy it, we can only transform it or transfer it. Okay, let's talk about something new, enthalpy, which is represented by the letter H. And enthalpy is the heat content of a system at constant pressure. Heat absorbed enthalpy is the heat absorbed or released by a reaction at constant pressure, and it's the same as the change in enthalpy. Heat absorbed or released by a reaction at the constant temperature is the same as the change in enthalpy, so delta H. What we're going to refer to most when we talk about thermochem is delta H, or change in enthalpy. Exothermic reactions have a negative delta H, whereas endothermic reactions have positive delta H. And what this means, and we get this partially from Q systems is equal to negative Q surroundings, because Q and delta H actually do have a relationship. But exothermic reactions have negative changes in enthalpies, and endothermic reactions have positive changes in enthalpies. And again, because the universe is in itself a whole thing and you can't create or destroy energy, Q system is equal to negative Q of surroundings. With that in mind, we can relate all of these together to say that Q system is equal to delta H, which is equal to negative Q surrounding, which is equal to negative mc delta T. Alright. So Q systems, Q surroundings, and delta H's. Oh my. All right, there's a lot to be going on here, so let's slow it down for a minute and take a look. Experimentally, we are measuring Q surrounding because measuring Q system is incredibly difficult. It's a very small part. So experimentally, we get and measure Q of surrounding. That's what we're measuring. But delta H is always calculated in terms of Q system, as the heat of enthalpy is the heat of the system, not of the surroundings. So, since we normally calculate Q system when calculating delta H, we need to actually calculate negative Q surrounding, as Q system is negative Q surrounding, or alternately Q surrounding equals negative Q system. So, what that means is that our delta H is actually equal to negative Q surroundings. This is why delta H is going to be negative for exothermic reactions and delta H is positive for endothermic reactions, because we measure the delta H of surroundings. So when something gives off heat, our change in temperature is positive, giving us a positive Q surroundings, but it's an exothermic reaction, so delta H is negative Q surroundings, so negative of a positive is negative. Whereas with an endothermic reaction where the change in temperature is now negative, because heat is being removed from the surroundings into the system, that negative delta T gives us a negative Q surroundings. The negative of a negative is a positive, which is why delta H is positive for endothermic reactions. So it kind of makes sense. So let's look at a question. When you have 25 mils of water containing 0.025 moles of HCl at 25 degrees Celsius, when that's added to 25 mils of water containing 0.025 moles of sodium hydroxide, also at 25 degrees Celsius, in a calorimeter, a reaction occurs. Calculate the enthalpy change in kilojoules during the reaction if the final temperature is 32 degrees Celsius. Assume the density and specific heat of both solutions is 1 gram per mil and 4.18 joules per gram degree Celsius, respectively. So let's look at that information again. So we've got 25 grams of water with 0.25 moles of HCl at 25 degrees Celsius, 25 grams of water with 0.25 moles of NaOH at 25 degrees Celsius. During the reaction, the temperature rises to 32 degrees Celsius, and we're supposed to figure out what the enthalpy of the reaction is given C is equal to 4.18 joules per gram degree Celsius. So let's identify our variables, identify our equations so we can identify our variables. We know that Q system is equal to delta H, which is equal to negative MC delta T. So we know that delta H is equal to negative MC delta T because Q system is equal to negative Q surroundings. So we need to find delta H is equal to negative MC delta T. So we need to find a mass, a C, and a delta T. So if we look here, we've got 25 grams of water twice. So those two added together, that's our mass. And then we've also got an initial temperature of 25 degrees Celsius for both of them. So that's our TI. And we're told that the temperature raises to 32 degrees Celsius, which is going to be our TF. TF minus TI is delta T. And we've also been given a C of 4.18 joules per gram degree Celsius. So we know M, C, and delta T. So all we need to do is just plug in those numbers. So delta H is going to be equal to negative, and then we say 25 plus 25 grams times 4.18 joules per gram degree Celsius times 32.0 degrees Celsius minus 25 degrees Celsius. And you get negative 1,463 joules. But they asked for the answer in terms of kilojoules. So if we divide by 1,000, we're going to get it in terms of kilojoules. And so our answer is that the change in enthalpy of this reaction was negative 1.46 kilojoules. Okay, not too hard. We're just using Q in a different way now. So chemical reactions and enthalpy change. In a chemical reaction, enthalpy change can be written as either a product or a reactant, dependent upon if the reaction is exothermic or endothermic. If the enthalpy change is considered a product in an exothermic reaction, meaning that heat is given off. So heat is given off or put into the surroundings from the system in an exothermic reaction, so heat is a product. It is produced from the reaction. Whereas in an endothermic reaction that's taking heat in from the surroundings into the system in order for the reaction to occur, in that case heat is a reactant. It is dependent, the reaction requires that heat in order to actually occur. So we can actually write these in terms of a chemical reaction. We can include this enthalpy change in our chemical equations. So if we had calcium monoxide here, or calcium oxide, sorry, monoxide, really. Calcium oxide and water, we're going to make calcium hydroxide, and that's going to release a little bit of heat. So we create calcium oxide plus water, making calcium hydroxide plus heat, because we have delta H over here as a product. Since it is a product, it's exothermic, which means that our delta H is going to be negative, so we can also write it as calcium oxide plus water, making calcium hydroxide, with a delta H of negative 65.2 kilojoules. Okay, so if delta H is a product, it's an exothermic reaction, which means its delta H is negative. If it is a reactant, it's an endothermic reaction, and therefore the delta H is positive. So let's do an example. If I was given this equation saying that 2 sodium bicarbonates, or sodium hydrogen carbonate, plus 129 kilojoules of energy makes sodium carbonate plus water plus CO2. And I was asked to write this in terms of a chemical reaction with an a thermochemical delta H written next to it, I would write 2 NaHCO3 making Na2CO3 plus H2O plus CO2 with a positive delta H, because again, 129 kilojoules was a reactant this time, which means this is an endothermic reaction, which means that my delta H is positive. If I then asked, given the reaction above, what is the enthalpy change for 2.75 moles of sodium hydrogen carbonate, I would need to do a little bit of calculating, because this 129 kilojoules is for this reaction as written here. According to this reaction, I only have 2 moles of sodium hydrogen carbonate. But what if I had more? What if I had 2.75 moles? And so you would solve this very much like we've solved any unit conversion problem or stoichiometry problem. We're going to start with what we know. We know that we have 2.75 moles of sodium hydrogen carbonate. And from our reaction, we know that for every 2 moles of sodium hydrogen carbonate, we have or create or need 129 kilojoules of energy. So 2.75 divided by 2 times 129 kilojoules gives us 177.375, or 177 kilojoules as the answer. Now you can go back and double check this by seeing if it makes sense by looking at the problem. So in this reaction, I had 2 moles of sodium hydrogen carbonate, and that required 129 kilojoules of energy for the reaction to go. If I have more moles, so more amount of sodium hydrogen carbonate, I should require more energy in order to get this reaction to go. I should require more enthalpy change in order for the reaction to happen, which it's true, the enthalpy change for this is 177 kilojoules, which is more. Okay, so we've talked about heats and changes of reaction. What about in changes of state? So way back in Unit 4, when we were doing energy diagrams and looking at phase changes, we talked about solids, liquids, and gases, or solids, liquids, and vapors. Now, there is heat required in order to go through all these changes. The enthalpy of fusion, which we talked about, is the enthalpy of going from a solid to a liquid. And then we have delta H, or enthalpy of vaporization, which is going from a liquid to a gas. Now, it makes sense that these should be positive because it takes energy. You have to put energy in to melt a solid into a liquid. If you're putting energy in, energy is a reactant, it's an endothermic reaction, the delta H is positive. Whereas we kind of tend to release energy in going from a liquid to a solid, which is negative delta H of solid. It explains why it's meant negative, because it's an exothermic reaction. It releases heat, or it releases energy in that case. Okay? Now, sometimes we talk about these in terms of molar heat of phase changes, and that's the amount of heat absorbed or lost by 1 mole of a substance as it changes phase. Because of this, 1 mole of a substance is, the units are always in kilojoules per mole, or per 1 mole, just like we do moles per liter or grams per mole in the calculating molecular weight. If we're talking about a molar heat of phase change, it's always kilojoules per mole. So let's do a calculation based on this. We can use these standard heats of phase changes to calculate different things. The amount of heat required to perform a phase change, the grams of a substance that will melt given a specific amount of heat, etc. So if I asked how many grams of ice at 0 degrees Celsius will melt if 2.25 kilojoules of heat is added, we can calculate that. Knowing that the delta H of fusion of ice is 6.01 kilojoules per mole, and that the molecular weight of water is 18.015 grams per mole, we can start with what we know and go from there. So we want to know how many grams of ice will melt if you put in 2.25 kilojoules of heat. So 2.25 kilojoules of heat is added, which means it's a reactant. So if we write out the equation for this, we're going to have water as a solid plus 6.01 joules per mole going into water. I think I made a mistake here. No, that's right. So we know that the delta H of fusion, so the delta H, the enthalpy required, is 6.01 kilojoules per mole to make 1 mole of ice into 1 mole of water. But the question is, how much or how many grams of ice if I just added 2.25 kilojoules? So less, okay? We need 6.01 kilojoules for 1 mole. Okay, well, how much do we need? Or how much would we melt if we only use 2.25 kilojoules? So we're going to start with the mass, or to solve for mass of ice, you're going to start with our kilojoules, 2.25 kilojoules, multiply it by our kind of almost chemical reaction, almost multimole ratio here. We know that for every 6.01 kilojoules, we have 1 mole of ice, and then multiply that by the molecular weight to get rid of moles and solve for grams of ice. And you actually get 6.74 grams of ice. Now we know that there's 18.015 grams of ice in 1 mole, so the fact that there's 6.01 kilojoules in 1 mole, 2.25 is about a third of 6. 6.74 grams is about a third of 18. That kind of makes sense, that if you only put in a third of the heat to try and melt the ice, you're only going to be able to melt about a third of the amount of ice. Okay, you can kind of calculate and back check yourself there. Okay, let's talk about heats of solution. During the formation of a solution, heat is either released or absorbed. So we've been talking a lot about chemical changes, but let's talk in like chemical reactions. But in making a solution, so in making a 1 molar HCl solution or that sugar solution that you guys made in lab, it either required heat to form it or it released heat, and you've seen that. So the enthalpy change is called the molar heat of solution, and it's representative of the heat released or absorbed caused by the dilution or dissolution, so the dissolving of 1 mole of substance. This is the reaction that is occurring in disposable hot or cold packs, where hot packs are formed from an exothermic reaction and cold packs are formed from an endothermic reaction. So both of these are where we're taking a solid and we're dissolving it in a solvent. So we're taking a solute and dissolving it in a solvent to make a solution. And you can either release heat in that or you can require heat. And so cold packs are situations where you're requiring heat, which is why they have an endothermic reaction and why they feel cold to us, whereas hot packs release heat, and that's why they feel hot. Okay, so I know that this was a lot to do and a lot to look at, so kind of mull it over tonight, and we're going to talk more about it tomorrow and get more into some of the trickier parts of thermochemistry, like Hess's law. So get excited. Have a good night, guys.